This video is part 3 of an ongoing series. Click on the link at the top right or go to the link in the description for parts 1 and 2. You can also subscribe to the Project Masquerade channel for updates on future videos. Last time we explored the simple field map and began constructing our movement and parkour so that we can get around this environment in a more involved way than simply running around a relatively empty space. But that was only the beginning, only the foundation upon which we will build the true meat of this system. Today, we'll be looking at the more vertically challenging hike map, and how we can further develop our parkour system to conquer it. Welcome to Game Mechanics Explored. In the last video, we made as many movements as we could that could occur below our height boundary. With that out of the way, we only have one movement to make above that boundary, mounting ledges. Before, if a ledge was low enough, I simply allowed the player to climb up and onto the platform, since they can't really hang from something that goes below their knees. With our platform scanner able to find a point above the player's head with enough clearance to hang from, we can press X to trigger a new movement, and nothing happens. As I said before, the player doesn't know what is in front of them and needs to rely on the platform scanner to give it information. They also don't know what they're doing either. I'm not an expert in programming, but if I know anything, which I don't, it's that unless you tell the computer to do something, chances are it'll do the exact opposite. The first thing we need to do is to take this point here and get the player to move to it. Unity has this neat little function called slurp, or spherical interpolation. It sounds complicated, but all we need to know is that it takes an object from one point to another in a spherical motion, meaning that we get this nice curve to the movement. This is as opposed to lerps, which move in a straight line, which also works fine but looks kind of weird. We can now use this scan point and set it as the endpoint for our slurp function. I also set the actual endpoint a little bit lower than the scan point, because the point the player moves around is based on their origin, so rather than the player's hands moving there, it will actually move their feet there, because that's where the origin is. We also want the player to animate. It'd look a little weird if they just hovered upwards. In our animations, I have an idle animation for hanging from a ledge, and I have a couple of animations to transition the player from an idle standing pose to that hanging idle pose. I'm blending two of them together using a blend tree so that the player will animate correctly even if the platforms are at differing heights. We already know how high these points are from the ground, so we can use that value to blend between the two transitioning animations. Now that the player can animate properly while moving to the point that we found earlier, we have a couple more settings to consider. Despite using our angle boundary from the last video, the player needs to be at the correct angle when hanging from a ledge, otherwise it would look pretty silly. And we can't just set the angle boundary to something ridiculously accurate, otherwise it would be too hard for the player to actually get that correct angle. Using the platform scanner, we can get what is known as a normal of a given surface. The normal of any surface is the direction perpendicular to the surface itself. It's hard to explain in writing, so on screen you can see the player facing various parts of this cylinder. The platform scanner is sending out its sphere casts, and those casts are returning a scan point that we want to use to move our player to, shown here as the red sphere. It's also returning the normal of the surface that it scanned, shown by the red line. Now, there's a bit of a problem here. Normals are classed as vectors in code, which are practically 3D coordinate values. We need to set our player's Y rotation, which is an angle, a single number. So how do we turn this into something we can use? Well, there's another neat little math function called ATAN2, short for 2 argument arctangent. Again, it's complicated, but all we need to know is that by feeding the x and z values of our normal into this function and converting the results from radians to degrees, we get an angle. Because the platform scanner is running constantly, we always get the angle that we need, because we always have the normal that we need. As you can see, if we go back to the wall, face it, and let the scanner do its thing, we now have an angle to apply to our player's Y rotation. We now have a position and a way to move to it, an angle and a way to rotate to it, and a nice set of animations to tie it all together. Now we can trigger the movement with the X button. Ladies and gentlemen, let me introduce you to the character controller component. Remember last time when we programmed our movement? Well, we didn't really program any movement specifically. We set up a few equations that calculated things like speed and direction, and then simply fed those values into the character controller. It does all the heavy lifting when it comes to the real movement calculations. What I didn't mention last time is how we also calculated the velocity produced by gravity when we fall. I don't know if this actually affects the character controller on our end, but the result is that this component seems to affect our player in ways that we don't want it to, namely making us fall to the ground. Remember, the player isn't really hanging from this ledge, the code just tells them to go to a position and stay there when they're idle. But because the character controller wants the player to fall down, they fall down, regardless of what I'm telling the player to do. This component seems to take priority. You might think that changing our gravity to something like 0 would solve this, but it doesn't. You might think removing any mention of it in the code would work, but it doesn't. While the character controller is active, it always seems to affect the player, and I really don't know how to fix this in an elegant fashion. The best method I found was to just turn the whole component off whenever I transition the player to a climbing state. The character controller can't affect my player's position if there is no character controller. It works, but it's not an ideal solution, and I'm still going to try and find a workaround for it. However, with that out of the way, we can now get our player climbing around on these walls. The old setup for the platform scanner isn't going to work here. Before, we really only wanted to scan the wall directly in front of us so that we could receive information and interact with it based on that information. Now, we're attached to that wall, and we aren't going to get anything useful from a wall that's 2 inches from our face, especially since we're trying to move around the whole surface of said wall. This is where past attempts at this system have failed. Before, when my programming knowledge was even worse than it is now, I barely had any idea of how to use raycasts, and I didn't even know sphere casts existed. I had to use different methods of moving the character around walls. I had this horrible system that would generate a load of points along some ledges, and then find the relationships between those points so that I could use that information to tell the player to move around. Even though these old methods ultimately failed, I learned a lot about how important directions were to this system, and how I should go about calculating them. Despite the old method's problems, not much has really changed in retrospect. Instead of generating these points and moving the player along a predetermined path, the player now finds those points dynamically with the platform scanner. As I said before, there isn't a gold standard to how this system should be programmed. But if I had to pin it to something, it would be this. Parkour is just another way of moving, and moving is just about getting from one point to the next. The standard here is finding the best and most efficient way to get the points that we need and interact with them in the right way. So, now that our platform scanner doesn't work while climbing, surely we've yet again created the wrong method and have to start again. Well, not so fast. You might remember from last time that the scanner is set up by generating an array of origin points between two boundaries and casting the rays from those origins in a given direction. Now that we're climbing, these rays can still find points for us. We just need them to search for those points in a different way now. In my head, I'd imagine that most players, when climbing up walls in the likes of Assassin's Creed, point their analog stick in the direction that they want to go in. If we can convert those coordinates into a direction for a ray cast, and use the length of that ray to define two new boundaries for our scanner, then we'll be able to repurpose the platform scanner for both ground-based movement and climbing. This task was the very definition of easier said than done, and it took me about 2 weeks of constantly chipping away at the code to figure this out. The coordinates of the left analog stick are technically a direction, but I can't just take those values and plug them into the direction argument of a raycast. That direction doesn't account for the player's rotation. It's hard to explain, so I'll try and put it the best I can. When we have values like this, describing direction, position, rotation, scale, or anything like that, we often consider these values by default to be in world space. World space is just that, the space of the world around you, or more specifically, the values in relation to the world around you. These same values can also be expressed in local space, or the space as it relates to a particular object, for instance. This game object and its coordinates are shown in world space, with each coordinate representing how far away this object is from the world origin along each axis. But if I took this game object and made it a child of this empty game object right here, its coordinates are now shown in local space, because its origin has changed. When we take our left analog stick's direction, the engine and the code assume that its direction is in world space. So, if I point the analog up or down, everything is fine, because for both the world and the player, up and down is always the same and will always be the same. Left and right, however, aren't the same. If my player's Y rotation is 0, and I point my analog stick to the left, sure enough, the ray points left. If my player's rotation is, say, -90, and I point it to the left now, it's wrong. Notice, however, that the ray is pointing in the same world space direction as it was last time. This is probably the most important thing to remember. It's not really pointing left, it's more so pointing west. Our player's rotation needs to be factored into this to ensure that the ray will always point in the correct direction, a direction true to the player's local space and not the world's. We need a big equation that converts this direction into a new one. I'm just going to show it on screen and describe what happens. It won't make sense, it's probably not the best way to do it, but by golly it works, and that's the most important thing. First, we create a modified Y rotation. We do this by finding the arctangent of the sine of our Y rotation in radians and the cosine of our Y rotation also in radians. We then take this result, convert it back into degrees, and add 90. With our modified Y rotation, we can begin constructing new X and Z values for the new direction. Our new x coordinate is made by multiplying the left analog stick's x coordinate by the sine of our modified y rotation converted back into radians for some reason, and the new z is the same except for a cosine. As stated before, the up and down directions are correct to what we want, so the y coordinate of our new direction is just the y coordinate of the left analog stick, whereas the x and z coordinates are the ones we just made. All of this long-winded crap means that the ray will point in the direction that we want it to, no matter what way the player is facing. If you want to program something similar, I've just put the code on screen because I don't want you to suffer like I have suffered. After all that, we use the same method as before to actually retrieve our point from the platform scanner, and now we have a way of actually scanning the wall and getting ourselves a point to move to. Now that we're hanging here and doing nothing, it's about time we start climbing around this wall. Luckily, the code is very similar to the code we used to get ourselves here. We have a point from earlier and the rotation that we need. One thing to note here is that we need to blend our animations again. To get the full range of 360 degree climbing, we blend together these 10 animations of varying angles. We do this by finding the angle that we're actually moving in. We can find this angle a couple of different ways, but the simplest for me is to just take the coordinates of my left analog stick, feed it through the arctangent function again, and then convert the result from radians to degrees. We can plug this angle into the animations so that we can smoothly blend between them. Now all we need to do is point our analog stick in the direction we want to go and press X. We can tighten up our code a little bit further by only scanning for a certain layer, meaning the scanner will only take viable geometry into account. I've had problems before with the platform scanner latching onto things that I don't want it to and having the player climb on objects that shouldn't be accessible, so this will help make the system just that little bit more accurate. I also wanted to be able to take distance into account and have that alter the way the player moves. Farther platforms and ledges require more of a wind-up to launch the player over there, and this is communicated entirely through animations. I have these 10 animations and nothing more, so I'm not currently able to add this in, but it's worth noting that further work can be done to really sell the movements here. I'm always conscious that some of the movements don't look quite as they should, and the wall climbing animations are one of the best examples. Whether it's down to the code or the animations still remains to be seen. It's now time to get our player back onto solid ground. When we're hanging here and ready to climb up, we must always remember that the player doesn't know squat about anything. I mean, look at him. We need to find a way of telling the player that they can climb up here. Our code is also starting to get a bit long, so we want to use as much information that we can retrieve from the platform scanner as we possibly can. If we're going to climb up, chances are we'll also be pointing our analog stick up, and there's a couple of checks we can perform right there. While we have our analog pointed up here, our platform scanner is also pointing up here. And in this big empty space that we want to climb onto, the scanner isn't finding anything. The data that we get from the scanner returns in a very particular way if it doesn't find anything with the parameters I've set. The main thing we want to check though is this value right here, lateral scan, the x and z coordinates of the final point that gets returned to us. If the platform scanner actually finds something, no matter which ray hits it, this lateral scan will be updated. If nothing is found, it gets set to 0. While this value is 0, we can perform another check on the left analog stick, affirming whether or not the analog's y coordinate is above a certain threshold, meaning the player is pushing up on the analog and trying to dismount onto this ledge. If both checks return true, then we can be pretty certain that we can climb up. Again, the player doesn't know exactly without massive amounts of extra code, so just being sure enough should be fine for now. After all that, climbing up is as simple as triggering the animation and letting it pull the player onto the edge. This is because the animation has something called root motion, which physically changes the player's coordinates while it plays out, rather than the player's position being unaffected. There are some situations where having no root motion is useful, but in this case, it does the work for us, meaning we don't have to set up any additional code for the movement to work. I did have to push his initial position upwards just a little bit to help the animation, but that's about it. While we're in this animation, we can begin transitioning the player back to their original grounded state from before they started climbing, which pretty much just involves turning the character controller back on. And that does it. We're now able to get the player from the ground to the top of the platform by climbing. And we're able to use the platform scanner again, showing just how versatile it can be when used properly. However, our boy is now stuck up here, so just like last time, what goes up must come down. Let's take a look at this. Remember way back 10 seconds ago when I was talking about how versatile the platform scanner was? Well, sometimes it isn't. And for some movements, we need to create a couple extra measures to get the information that we need. While we're in this grounded state, we know that the platform scanner casts its rays forward from the player to find walls and platforms. When we need to find a ledge below the player, it would just be more inefficient to try and work that into the platform scanner itself, especially when the solution is pretty simple. In the last video, we made the player stop at the edge of platforms to stop them from accidentally falling off. While this effect is active, we can initiate another raycast below the player's feet and cast it back towards them. This raycast will find a point below our player's feet and give us a new point to keep our player in place while we climb back down. The code here isn't too dissimilar from the code for mounting ledges. Again, we set a position and move to it. We set a rotation and trigger an animation. Because we're transitioning to a climbing state again, we turn off the character controller as well. You might notice that these movements all have a pretty similar execution within the code. A lot of things that almost use the same ideas, and on occasion they use the exact same terminology. Whenever I can, I want to try and streamline my code. The current iteration is actually a remake of the previous because it had become practically unreadable and editing it would have taken longer than just building it all over again. I'm not really worried about the code slowing down the game. It's only one script that's about 1,000 lines long, and the only processor heavy part is the raycasts. Even then, I'm only running a maximum of about 25 maybe. And I know from previous testing that Unity can run the platform scanner at nearly 5,000 raycasts before the frame rate drops below 60. I want to point out that optimizing code isn't just about making it more efficient, it's very often just as simple as making it easier to work with. Before, the previous version did work properly, but it was a mess, and it had become harder and harder to fix bugs. I want to try and optimize things as much as I can in this script to avoid falling into that trap again. Last time we had all those vaulting movements over low platforms. There were about 7 variations of these platforms that could be discerned by the scanner, but the actual code that pulls these movements off is all contained within one method. Just by considering how our code is sorted and structured, we have massively improved our code. And while a lot of you might not agree with my rampant use of nested if statements, it makes bug testing a breeze. The checks for those 7 variations and the one method they reference are actually smaller than my old method, which only found 2 variations and had to be kept in 2 separate methods. The checks will pretty much always be different. That's the nature of the system. They need to be different to categorize different kinds of platforms. But if the code that we use to interact with them is basically the same every time, then why would we write the same code over and over again? It's much more efficient and a lot more streamlined to take that little chunk of code, put it in a method, and just call for it when it's needed. When it comes to these climbing transitions, these movements can be sorted and streamlined in the exact same way. Some of these movements come from stuff we'll program in the next video, but I was able to take 5 more movements and contain them in one very small method. Many times though, trying to streamline code is an uphill battle, and sometimes it just can't be done, such as in the case of our next movement. We can attach to a ledge, climb to the top of this wall, climb onto it, back into a standing position, and then turn back and drop into a climb, all with a few simple checks, and one small method. Now that we're back at the bottom of the wall and looking to drop to the floor, the code that we actually use here isn't similar enough to the rest that we can actually fit it in. While the code isn't actually very long or complex, and just involves switching back to our climbing state and triggering an animation, we can't fit it in the method. I just wanted to point out that as much as I want to simplify the code for the future, sometimes it's just not as airtight as I'd like it to be. This script is still very much a work in progress, and a lot of work can be put into making this system something easier to return to in the future. I've mentioned before that I've had to put the system on hold because I lack the animations that I need to further expand it. One day, if I'm lucky enough, I'll be able to make those animations for myself. But because things aren't that simple, it could be a long time before I have the time, resources, or even skill to do that. I'm putting in the work now, so that not only can I come back to this system and understand what it does, but so I can also add new movements to the code without complicating it. I'm taking this almost modular approach to my game because it favours me in the long run. By at least having a specific formula for how a new parkour movement is created, I can very easily slot one into the script. All of the new movements will have a place in the current code. It's my job now to signpost those places for my inevitable return. Speaking of those new movements, there are a couple that I wanted to put into this section of the system in the future. I actually had this to an extent in the previous iteration of the code, but it wasn't fleshed out enough and I haven't reinserted it here. When the player is transitioning to a wall, climbing around or dismounting, they have to press a button, but we don't always want the player to have to do that. Bringing back those context inputs, I wanted the player to transition to a climb if they run into a wall with a viable ledge, rather than having to press X. The same can be true for other climbing movements as well. That's pretty simple stuff though. What happens if the player doesn't have a viable ledge to climb onto, and the player is still running full speed at a wall? I can't exactly stop the player from doing this, but I can add an extra movement to the system to account for it. If the player gets close enough to the wall while running, the player will try and run up the wall and will then drop back down again, shown better here in a game that actually has this movement. I want to add this movement because it will provide a ton of variety to the system. There are a number of movements that can spring forth from this one animation alone. Running up the wall could give just a little more distance to grab onto higher ledges and platforms, extending the height limit of the entire system. Maybe the player can jump backwards off the wall to a platform behind them. If they don't do anything on the way up, they can just slide back down. The sliding can be used to slow a player's descent down a wall with no platforms on it. It'll also allow for much more flexibility and variety to the system, with what should realistically be only 3 or 4 new animations. I can even get a wall jump mechanic out of it. Most of the code for this is actually already here, contained within methods I've already made, and sorted by checks that really aren't that complicated. I just don't have the animations. It's quite frustrating because I think this group of mechanics alone could nearly double the extent of the parkour system and give me so much more opportunity for interesting level design. All I can do now though is have everything ready to go. Another small addition was to the actual ground movement itself. Last time we were able to implement turning animations into the player's standard movement, and now that we have a little more verticality to our maps, I also wanted to implement a way for the player to more realistically interact with slopes. People don't exactly look like this when walking up and down slopes, and I wanted to give the player the ability to do that. Programming it shouldn't be difficult. Like last time, we were able to calculate a turning coefficient from the velocity of the player's rotation. I think we can do something similar here by crafting a coefficient from the angle below the player's feet. The character controller contains an angle limit variable, stopping the player from moving on slopes of a particular angle. It's no stretch then to assume that the character controller is already getting this angle somehow, and I plan to take it and use it for my own nefarious purposes. I don't know how I'd structure the animations in this mechanism, especially with the turning animations already here hogging up space, but I can cross that bridge when I get to it. We have now given the player the ability to climb some very basic structures, and further expanded upon their ability to interact with the environment around them. But basic is not enough. We can go even further. Join me next time when we will look at the most complex movements of the parkour system so far, and use them to explore our third and final map. Thank you for watching, and I'll see you next time.